Assalamualaikum. Hi everyone. The topic of my presentation is the design of microstrip patch antenna for 5G application using CST Studio Suite. Here is contents of my presentation. First, introduction. Next, problem statement. Then come with methodology. After that, I will go on to simulation result and finally conclusion. Let's start with introduction or background of research. The purpose of this project is to design a small antenna for 5G communication system antenna. The patch antenna have a frequency band of 26 GHz because 5G communication system will use three frequencies at 800 MHz, 3.5 GHz, and 26 or 28 GHz. The antenna using RT-derived 5880 substrate with dielectric constant value is 2.2 was designed and simulated by CST Studio Suite software to obtain antenna characteristic result. Moving on to problem statement. In line with the world wireless technology rapidity today, Malaysia does not want to be left behind in implementing 5G technology. Therefore, through the Malaysian Communication and Multimedia Commission (MCMC), the spectrum for frequency signal transmission had been set as 700 MHz, 3.5 GHz, and 26 GHz, with bandwidth allocated 3.3 to 3.8 GHz and 24.25 to 29.5 GHz for 5G implementation in Malaysia. Thus, researchers will focus on designing 26 GHz antennas for 5G communication system to enable small and compact antennas to be produced. Now, let's move on to my next topic, which is methodology. A flowchart on figure 1.0 is showing a process of how to design microstrip antenna. By using the CST Studio Suite software, the obtained values from the calculation process will enter into the software. The antenna design process begins with determining the ground design, followed by patch design. Then the simulation process is carried out. If the required frequency value is not successfully obtained, an optimization process needs to be performed. Once the required frequency values is obtained, the parameter analysis process will be performed. This is calculation formula we use to calculate and find the value of width, ground, length in width, effective length, and effective dielectric. Table 1.0 shows parameter list and figure 2.0 shows structure of the purpose antenna. Let's turn now to simulations results. The performance of design antenna determined by a few parameters such as return loss, voltage standing wave ratio, real power, and 3D far-field radiation pattern. Now I will focus on return loss. In the microstrip patch antenna design, we have achieved negative 35.357 dB return loss as shown in figure 3.0. The bandwidth is about 4.787 GHz. The bandwidth was determined by difference of 0.2 and 0.1, which the value of 0.2 is 27.891 GHz, while 0.1 is 23.104 GHz. It gives the bandwidth value from 23.104 GHz to 27.891 GHz. It almost precise with MCMC bandwidth value, which is 24.25 GHz to 29.5 GHz. Next, voltage standing wave ratio. Voltage standing wave ratio (VSWR) is a function of the reflection coefficient which describes the power reflected from the antenna. In the case of patch antenna, the voltage standing wave ratio should not be more than 2 and less than 1 along the bandwidth of efficiency. Ideally, it should be 1. As can observe from figure 3.0, the voltage standing wave ratio of purpose antenna is found as 1.0340. Next slide is real power. Figure 4.0a, b, and c describe the different real power for this purpose antenna. The accepted power is 0.4998 watt and power losses in dielectric is 0.1629 watt, while power losses in metals is 0.00189 watt. 3D far-field radiation pattern. Figure 5a shows 3D far-field radiation pattern for directivity gains at purpose antenna at frequency 26 GHz is 11.15 dB and the achieved directivity of design antenna is 7.406 dB at 26 GHz as shown in figure 5b. For conclusion, this antenna is good to use in 5G application. This is our references.